So now that we've taken a look at some Chemistry 20 review in terms of solutions, let's take a look now at some review in terms of acids and bases. Okay, just as a little reminder, here is a pH scale. Anything with a pH less than 7 is considered to be acidic. Anything with a pH greater than 7 is considered to be alkaline or basic. And what you'll see here is the pH right at 7 is what we consider to be neutral. So when we take a closer look at some acids, like I mentioned, they have a pH of less than 7. They're substances that react with water to form hydronium ions. Okay, now hydronium ions are something that we mentioned in Chemistry 20, and essentially what it is there's an extra hydrogen that has attached onto a water molecule, and this is what we called modified Arrhenius theory. And essentially what happens is that hydrogen breaks off from the acid and it's pretty strongly attracted to the water molecule in which the acid is dissolved in. Okay, the higher concentration of this hydronium ion in a solution means that it's a more acidic substance. So if we take a look at an example, okay, we have something like hydrochloric acid mixing with water. Now I like to write water, as HOH, just simply because we can see a little bit more what's happening. We have this hydrogen in our water that acts more like an acid, and this OH that acts more like a base in our water, and it gives us just a better understanding of what's going on. So essentially what happens is this hydrogen that I've highlighted in turquoise here, all right, it attaches on, once we dissolve this acid in water, it attaches on to this water molecule that's present to create our hydronium ion, which is H3O. Okay, the leftover ion is also present in our products here as just chlorine. Okay, when we do an ionization formula or any sort of replacement formula, anything like that, we want to make sure that both our mass and charge is balanced. So on this side we have a net charge of 0 overall, and on this side we have a positive 1 and a negative 1, also resulting in a net charge of 0. Okay, we have 3 hydrogens over here, 3 on the reactant side, 1 chlorine, and 1 oxygen. So we're balanced both in mass and charge, which we'll get further into as we go through some Chemistry 30 here. Okay, we can look at another example of a weak acid. Let's look at, for example, acetic acid, which is CH3COOH. Mixing with water again. Okay, and this time, this hydrogen here, it's the most convenient one to break off. He mixes with this water, again, generating our hydronium ion. Okay, and also left behind is this ion. And in this case, it's called the acetate ion. Okay, again, if we check charge and mass, we have a net charge of 0 on our reactant side, a net charge of 0 on our product side, and we have 6 hydrogens, also 6 hydrogens, 3 oxygens, 1 carbon, I think we're good. So what you will learn, or what you may have learned in Chemistry 20, is that strong acids, such as my top example here, these acids like to dissociate or form this hydronium ion nearly 100% of the time. So above our reaction arrow, we can put the 100% sign, or approximately 100%, and that's because that reaction likes to form these products, H3O and Cl-, nearly 100% of the time. Anything that's a weak acid is going to depend on what the acid is in terms of the reaction percentage. Now, generally, we can notate it as kind of a less than 50% will react, but it is, like I said, dependent on that weak acid to see what percentage it will react to form both our H3O positive and our CH3COO in this case. So as you can imagine, since the higher concentration of hydronium ions makes a more acidic substance, if this top reaction, which is our strong acid, is occurring 100% of the time, there will be more hydronium ions present, meaning that it becomes a more acidic substance. Okay, inversely, our weak acid, Okay, it only happens less than 50% of the time, producing less hydronium ions, again, making a slightly less acidic substance. It's not saying that it's not acidic, it's just saying that slightly less, or depending on the acid, it is less acidic than this H3O that's produced in our strong acid example. Okay, when we take a look at bases, like I mentioned, have a pH of greater than 7. Substances that react with water to produce hydroxide ions. Again, this is something that should be familiar to you from Chemistry 20. And essentially, if we're looking at something like sodium hydroxide, NaOH, we can basically look at a simple dissociation reaction where we have sodium ions and hydroxide ions formed. And again, this component here is our basic component, making it a base. Okay, and again, the more basic means the more hydroxide there is present. This example here, again, is considered to be a strong base, which just likes to dissociate approximately 100% of the time. We also have some weak bases that we can talk about further in Chemistry 30, like, for example, ammonia or bicarbonate ions, which act as a weak base, and they also produce small amounts of these hydroxide ions. Okay, now let's get into some math stuff. So let's get into some calculations. These two formulas should be quite familiar with you from Chemistry 20. So to calculate pH, we use the negative log of your hydronium ion concentration. Now, this hydronium ion concentration should be, in fact, in moles per liter. Okay? And same with this, we should have our concentration in moles per liter in order to type it into our calculators accurately. Okay, now these two formulas are the exact same, just the inverse of each other. So just like we rearrange formulas using multiplication, division, things like that, this is the exact same formula, just rearranged to solve for the different entities. So the 10 to the exponent of pH is the exact same rearranged. It's just the inverse of this equation here. Okay. So pOH, again, is the same general formula. We have pOH equals the negative log of your hydroxide ion concentration. Again, this should be in moles per liter. And this also should be in moles per liter that you're calculating. All right, now pH and pOH do not have units. It's just a simple number that you have to record. Now, if you were to type this into a calculator, that would be a TI-83 or a Texas Instrument calculator, you would be typing this in as the negative button. All right, for this, sorry, I should clarify, for this first reaction. Okay, negative, and then the log button. Okay, and then your hydroxide ion concentration. So your number, whatever number that might be. Okay, this equation here, all right, you should be typing in the second function button. All right, and then you should type in the comma button. Okay, that will give you the 10 exponent number. Okay, and then you will type in the negative and then your number. So if you have a TI-83 calculator, those are your two formulas. Those are the buttons that you need to push in order to solve for these accurately. Okay, a few more calculations. You likely would have seen these from Chemistry 20. All right, the first one being, if you have a pH and a pOH, it should equal 14. The reason being is that generally our pH scale goes to 14, 0 to 14. So when we add these two numbers up together, they should equal a total of 14, this number here. So we can use a little bit of this simple math function to help us out through some of our problems. Okay, we can also use the water ionization constant. Now, essentially, the water ionization constant, this value here, the 1.0 times 10 to the negative 14, gives us an indication as to how frequently water will collide with itself to ionize into OH and H3O. So essentially what this means is you have two water molecules, so two waters, and they just collide at the perfect place to form one hydronium ion and one hydroxide ion. Okay, essentially one of these hydrogens from one of these waters broke off to form H3O, and the resulting molecule that's left behind is OH. And essentially this reaction will happen very, very rarely. In fact, 1 times 10 to the negative 14 this reaction will occur. Now, we can consider that because it can help us to solve for our hydroxide or hydronium ion concentrations dependent on our acid or base. Okay, and this is partly due to this relationship of pH and pOH, again, equals 14. Okay, so we can rearrange this formula where Kw is equal to 1.0 times 10 to the negative 14 if we have either our hydroxide ion concentration or our hydronium ion concentration and this known value of 1.0 times 10 to the negative 14, okay, we can solve for the other unknown variable, which is kind of handy. Okay, let's just kind of hammer through some of these practice questions, and we'll see how quickly we can get through them. And then there's just some practice questions on a worksheet at the end of this lesson that you can work through just to make sure that your skills are top-notch as we go forward into Chem 30. Okay, so again, this gives you a hydronium ion concentration. So if we're given the hydronium ion concentration, we're most likely going to be looking for pH. So our pH is equal to the negative log of our hydronium ion. Okay, so this means that this is equal to the negative log of 2.1 times 10 to the negative 3. Okay, and when I plug that into the calculator, we should get a pH of 2.67. Now, remembering some significant digit rules, we should probably round this number to 2.7. Okay, simply because we are given two significant digits in our question, so we should probably leave our answer also in two significant digits. Okay, same formula goes for this solution down at the bottom. Okay, rainwater, we have pH equals negative log of our H3O. All right, and our pH equals the negative log of 1 times 10 to the negative 5 moles per liter, which should give us a pH of 5. Okay, I can look at this a little bit more simply. If I'm given beautiful rounded numbers, for example, 1 times 10 to the negative 5, this number here, okay, as long as I have 1 times 10, okay, as long as there's no other decimals here, like 2.1 for example, as long as this is a 1 times 10, this number as the exponent is going to be my pH. So you'll notice here, okay, the 5 here matches the pH 5 here, and that's simply due to our logarithmic pH calculation. Okay, this one's going backwards. We're going from a pH and we're going to be calculating our H3O ion concentration. So in this case, our H3O, or our hydronium ion concentration, is equal to 10 to the negative pH. All right, I'm just going to make this a little easier to read. Okay, so 10 to the negative pH. So what we do this time is we have 10, and we're putting to the negative pH, which is negative 11.3. Okay, now this pH is quite basic. Okay, so when we plug it into our calculator, we should expect to see a fairly low hydronium ion concentration. We want to see quite a small number, because if we don't have a low number, it's going to be an indication that we might have done our calculation a little wonky. So when I type this into my calculator, I get 5.01 times 10 to the power or exponent of -12. Okay, and this is in moles per liter. We have to be careful, there is a unit on this number because we're looking for a concentration. All right, and like I mentioned, the number 5.01 times 10 to the -12 is quite a small number, which is what we expect when we see a sort of a high pH. Okay, again, this is a basic pH. Again, let's solve for this bottom one. Our hydronium ion concentration is equal to 10 to the -2.65. And when I plug that in, okay, I get this number equaling 2.24 times 10 to the power of -3 moles per liter. Again, try and remember your significant digit rules. Again, notice the two values that we've just solved here. So the difference between the pH of 11.3 and 2.65 is quite significant. Okay, we're working with numbers that are very low hydronium ion concentrations to relatively a bit higher for a higher pH, which is what we expect. Okay, here's some base calculations that we're looking at. Okay, we're going to calculate the pOH of these. So our pOH, again, is equal to the negative log of our hydroxide ion concentration. So we have negative log of our 4.0 times 10 to the -8. Okay, this gives us a pOH of 7.4 for our pOH there. And again, negative log of our hydronium ion concentration, in this case 1.37 times 10 to the -6, gives us a pOH of 5.86. Okay, so now when we compare these two values, this is our hydroxide ion concentration. So this is what we expect to be a more basic, more or less basic. So if we compare the difference between milk and soap, with a higher concentration of hydroxide ions in soap, we would expect a greater pOH. We would expect this substance to be more basic, which we do. We get a more basic substance, okay? Remember that your pOH scale is inversed or inverted from your pH scale. So something that has a low pH has a higher pOH, and something that has a high pH has a lower pOH, which is what we see here. Okay, if we carry on to our other examples here, in this case, we're going to be calculating our hydroxide ion concentration, which again is equal to 10 to the exponent of negative pOH. Okay, so in this example here, we have 10 to the negative 9.8. You'll notice that these equations are identical to our pH calculations. We get this equaling 1.5, or 1.6 we'll go with. 1.6 times 10 to the negative 10. Okay, like I mentioned, a high pOH, we expect it to be quite acidic. So we expect our hydroxide ion concentration to be relatively low, which is what we see here. And again, our last example here, 10 to the negative 0.25, which means that this entity is quite basic. Okay, our hydroxide ion concentration is 5.6 times 10 to the negative 1. So again, relatively, our bottom entity has much more base in it than the first example. So this is carbonated pop. We know that carbonated pop is often quite acidic, which is what we see, and our relative value of our hydroxide ion concentration is significantly lower than our oven cleaner, which has a pOH of 0.25 or is very basic. Okay, here's a little bit harder of a question. Okay, this is asking for both the pH, the pOH, and hydroxide ion concentration of a 0.24 mole per liter solution of hydrochloric acid. So this is definitely a multi-step question, and I'll try and break it up as best as I can here as we go through. So the first thing we need to look at is that hydrochloric acid, how does it dissociate in water? And essentially 100% of the time we get this formula, okay? 100% of it will form, of our hydrochloric acid, will form H3O and our chlorine ions. Okay, this is an example that I gave on a previous slide here. Okay, so what happens is whatever our concentration of our hydrochloric acid is in our example, which in this case they give us a 0.24 mole per liter solution, okay, I can automatically apply that value to this hydronium ion concentration because it dissociates 100% of the time. So I'll put that 100% on top. So you know why we're doing that, why we can use this 0.24 as a variable for our H3O. So I'm simply going to write that out. I'm going to say H3O ion concentration. Okay, again, square brackets, meaning concentration, okay, is equal to 0.24 moles per liter. All right. So when we take a look at this, all right, I can quite easily calculate my pH from this. I can say pH is equal to the negative log of my H3O, which is equal to the negative log of 0.24. Okay, so the negative log of 0.24 is equal to 0.6197 repeating. Okay, I'm just going to say 0.61, well, let's just say 62. Okay, so 0.62, this is equal to pH. Okay, lucky for me, there's a pretty simple calculation to calculate for pOH. So pOH, let's do this in a new color. pOH is equal to 14 minus my pH. So when I do that, this is 14 minus 0.62. Okay, this gives me 13.4 for my pOH. All right, and one more calculation. It's still asking for my hydroxide ion concentration. So when I go to do my hydroxide ion concentration, let's do this one in a new color also. Okay, my OH ion concentration is equal to 10 to the exponent of my negative pOH. So I take 10 to the negative 13.4. And I see that my hydroxide ion concentration is 3.98. Or I should probably round that to 4. So 4.0 times 10 to the negative 14 moles per liter. So when we take a look at our numbers, we just want to double check that they all make sense. We have an acid, okay, and the acid has a very strong or a very high mole per liter or concentration of our hydronium ions. With that said, this means that this is quite an acidic substance. We see that, and it's clarified with our pH. We see that our pH is very, very low, meaning our pOH is relatively high, and we see that our concentration of our hydroxide ions is very low, which is what we would expect here. So this is the last slide of our review for acids and bases and their calculations. And once you have gone through this, if you feel the need to pause or repeat any part of this mini lesson, please do so. And once you feel confident, there is a worksheet with some practice questions, followed by an answer key that would be given to you by your teacher. All right, good luck.